Chapter 8, Declaring Types and Classes. In this chapter, we introduce mechanisms for declaring new types and classes in Haskell. We start with 3 approaches to declaring types, then consider recursive types, show how to declare classes and their instances, and conclude by developing a tautology checker and an abstract machine. 8.1 Type Declarations. The simplest way of declaring a new type is to introduce a new name for an existing type using the type mechanism of Haskell. For example, the following declaration from the standard prelude states that the type string is just a synonym for the type list of lists of characters. Type string is list of char. As in this example, the name of a new type must begin with a capital letter. Type declarations can be nested in the sense that one such type can be declared in terms of another. For example, if we were defining a position as a pair of integers and a transformation as a function on positions, type pos is a pair of integers, type trans is a function from positions to positions. However, type declarations cannot be recursive. For example, consider the following recursive declaration for a type of trees. Type tree is a pair of an int and a list of trees. That is, a tree is a pair comprising an integer and a list of subtrees. While this declaration is perfectly reasonable with the empty list of subtrees forming the base case for the recursion, it is not permitted in Haskell because it is recursive. If required, recursive types can be declared using the more powerful data mechanism, which will be introduced in the next section. Type declarations can also be parameterized by other types. For example, if we were defining a number of functions that manipulate pairs of values of the same type, we could declare a synonym for such pairs. Type pair A is a pair of A's. Finally, type declarations with more than one parameter are possible too. For example, a type of lookup tables that associate keys of one type to values of another type can be declared as a list of key value pairs. Type assoc kv is a list of pairs of k's and v's. Using this type, a function that returns the first value that is associated with a given key in a table can be defined as follows. Find k is an instance of ek, and find is a function from keys a function that takes a key and an assoc, like a dictionary, and returns a value. Find kt is head of the list of v's such that the pair k prime v is taken from t and k is equal to k prime. Let's try that. Type assoc kv is kv, and then find I don't know why Emacs always indents my my Haskell code bad. So now, how do we declare a dictionary like this? Wait. God, my internet is really slow. So first maybe we should say L is it just gonna automatically know that it is of type assoc? We can do like hello world, goodbye hell. Find hello L. Oh yeah, it just works. Interesting. Because with strings, if I say like type hello, it doesn't say that it is of type list of char. But with the list, with this assoc, it doesn't say that. Like here, it doesn't say, oh, it's an assoc of strings. I don't know. 8.2, data declarations. A completely new type, as opposed to a synonym for an existing type, can be declared by specifying its values using the data mechanism of Haskell. For example, the following declaration from the standard prelude states that the type bool comprises two new values named false and true. Data bool is false or true. In such definitions, the symbol pipe is read as or, and the new values of the type are called constructors. As with new types themselves, the names of new constructors must begin with a capital letter. Moreover, the same constructor name cannot be used in more than one type. Note that the names given to new types and constructors have no inherent meaning to the Haskell system. For example, the above declaration could equally well be written as data A is B or C, because the precise details of the names are not relevant, other than the fact that they have not been used before. The meaning of names such as bool, false, and true is assigned by the programmer via the functions that they define on new types. Values of new types in Haskell can be used in precisely the same way as those of built-in types. In particular, they can freely be passed as arguments to functions, returned as results from functions, stored in data structures, and used in patterns. For example, given the declaration data move north or south or east or west. Functions that apply a move to a position apply a list of moves to a position and reverse the direction of a move. Functions that apply a move to a position, apply a list of moves to a position, and reverse the direction of a move can be defined as follows. Okay. Moves. So I think the function moves, couldn't that be written as a fold? I think so. Rev, move to move, and then it uses pattern matching. If you wish to try out such examples in GHCI, the phrase deriving show must be added to the end of the data declaration to ensure the system can display values of the new type. The deriving mechanism itself will be covered in later on. I think you made a typo there. In this chapter, when we consider type classes. The constructors in a data declaration can also have arguments. For example, a type of shapes that comprise circles with a given radius and rectangles with a given dimension can be declared by data shape is circle float or rect float float. That is, the type shape has values of the form circle r, where r is a floating point number, and rect x, y, where x and y are floating point numbers. These constructors can then be used to define functions on shapes, such as to produce a square of a given size, and to calculate the area of a shape. Because of their use of arguments, the constructors circle and rect are actually constructor functions, which produce results of type shape from argument of type float. as can be demonstrated using GHCI. Type circle takes a float and returns a shape. Interesting. So they're saying that constructors by default don't take arguments. That's very weird. The difference between normal functions and constructor functions is that the latter have no defining equations and exist purely for the purposes of building pieces of data. For example, whereas the expression negate 1.0 can be evaluated to negative 1.0 by applying the definition of negate, the expression circle 1.0 is already fully evaluated and cannot be further simplified because there are no defining equations for circle. Rather, the expression circle 1.0 is just a piece of data, in the same way that 1.0 itself is just data. Not surprisingly, data declarations themselves can also be parameterized. For example, the standard prelude declares the following type. Data may be A, is nothing, or just A. That is, a value of type maybe is either nothing or of the form just X for some value X of type A. We can think of values of type maybe as type maybe A as being values of type A that may either fail or succeed, with nothing representing failure and just representing success. For example, using this type, we can define safe versions of the library functions div and head, which return nothing in the case of invalid arguments, rather than producing an error. Save div, int, maybe int. Dividing by 0 is nothing. And dividing m by n is just dividing m by n. Save head, blah, blah, blah. 8.3, new type declarations. If a new type has a single constructor with a single argument, then it can also be declared using the new type mechanism. For example, a type of natural numbers, non-negative integers, could be declared as follows. New type nat is n int. In this case, the single constructor n takes a single argument of type int, and it is then up to the programmer to ensure that this is always non-negative. Of course, it is natural to ask how the above declaration using new type compares to the following alternative version using type and data. Type nat is int, data nat is an int. First of all, using new type rather than type means that nat and int are different types rather than synonyms, and hence the type system of Haskell ensures that they cannot accidentally be mixed up in our programs. For example, by using an integer when we expect a natural number. And secondly, using new type rather than data brings an efficiency benefit because new type constructors such as n do not incur any cost when programs are evaluated, as they are automatically removed by the compiler once type checking is completed. In summary, using new type helps improve type safety without affecting performance. 8.4 Recursive types. New types declared using the data and new type mechanisms can also be recursive. As a simple first example, the type of natural numbers from the previous section can also be defined in a recursive manner. Data nat is 0 or successor of a nat. That is, a value of type nat is either 0 or of the form suck, n, for some value n of type nat. Hence, this declaration gives rise to an infinite sequence of values, starting with the value 0 and continuing by applying the constructor function suck to the previous value in the sequence. In this manner, values of type nat correspond to natural numbers with 0 representing the number 0 and suck representing the successor function 1 plus. For example, suck 0 represents 1 plus 1 plus 1 plus 0 is equal to 3. More formally, we can define the following conversion functions. Nat to int, and int to nat. For example, using these functions two natural numbers can be added together by first converting them into integers, adding these integers, and then converting the result back into a natural number. However, using recursion, the function add can be redefined without the need for such conversions, and hence more efficiently. I doubt that. This definition formalizes the idea that two natural numbers can be added by copying suc constructors from the first number until they are exhausted, at which point the 0 at the end is replaced by the second number. For example, showing that 2 plus 1 is equal to 3 proceeds as follows. Add suc 0 suc 0. Applying add. Wait, let's look back at add. So if you're adding something which is a successor of something else, then you just do the successor of the sum of the m and n. Okay, as another example, the data mechanism can be used to declare our own version of the built-in type of lists, parameterized by an arbitrary type. Data list is either nil or cons A to a list. That is, a value of type list A is either nil, representing the empty list, or of the form cons x to x's for some value x of type A and x's of type list A, representing a non-empty list. Using this type, we can then also define our own versions of library functions on lists, such as to calculate the length of a list. While lists are one of the most commonly used data structures in computing, it is often useful to store data in a two-way branching structure, or binary tree, as depicted in the following example tree. Image, yeah, I can't open that, I think. In this example, the numbers 1, 4, 6, 9 appear at the external leaves of the tree, and the numbers 5, 3, and 7 appear at the internal nodes. Using recursion, a suitable type for representing such trees can be declared by data tree A is a leaf A, or a node of two trees and a value A. And the tree pictured above can be represented as follows. T is of type tree of ints. Maybe if I say here L is of type assoj string. Yeah, okay. But with strings, it picks the type alias over the actual type without you having to declare that it's a string, which is interesting. We now consider a number of functions on such trees. First of all, we define a function that decides if a given value occurs in a tree. Maybe I should have opened this in a web browser instead of here. But yeah. That is, a value occurs in a leaf. Okay, let's just try and write that. Kind of ambitious, but data tree A is leaf A or node tree A tree A. Oh. Variable not in scope O. Where did I type in O? Oh. Oops. So now it can be like leaf 0. What? What is that? Oh, because 0 is not per se an integer. Like it could be something else. And what if we do node 0, 1, node 5, these need to be leaves. Wait, leaf. Bam. That's pretty cool. Now, we consider a number of functions. First of all, we define a function that decides if a given value occurs in a tree. Let's try that. So occurs in takes a value a and a tree of a's and gives back a bool. Occurs in 0 leaf. Oh wait, this should be x, y. Is x is equal to y. And then, can we run that already? Oops. Oh yeah, we should say, how do you write that? So a is not necessarily able to use equals equals. Okay, I think it's like this. Ec a. Okay, that's cool. Occurs in 0 leaf 0. Occurs in 1 leaf 0 false. Okay, then occurs in x node t1 y t2. Now I think we write it like this. Yeah? So if x is equal to y, we'll return true. Kind of ugly to return true. Otherwise, if x, I don't know, if occurs in xt1, return true. This is just a giant or statement that I'm writing here. But let's finish what I was doing. Occurs in xt2 is true, otherwise is false. Yeah, and let's define a little. Let's see. T is a node, and a node, and a leaf 3. And then 1 leaf 4. So that's the left tree. Then 7 node leaf. Maybe it shouldn't be symmetric necessarily, as I'm writing it here. And let's just, for easy, tree of int. Okay, and then we can say occurs in 0 t, false. Occurs in 3 t, true. So I think it works. But let's try rewriting it as an or statement. So this is just what? Equal to is or just, yeah, or this or this. Oh yeah, and then we, okay, wait, let's see if we can wrap it. And then these can be gone. Oh. Boom. That seems to work. How elegant. That is, a value occurs in a leaf if it matches the value at the leaf, and occurs in a node if either matches the value at the node. If it either matches the value at the node, occurs in the left subtree, or occurs in the right subtree. Note that using lazy evaluation, if either of the first two conditions in the node case is true, then the result true is returned without the need to evaluate the remaining conditions. In the worst case, however, is that really lazy evaluation? I think that's just short-circuiting. In the worst case, however, the function occurs, oh, they called it occurs, okay, whatever, may still traverse the entire tree, in particular when the given value does not occur anywhere in the tree, period. Now consider a function that flattens a tree to a list. If applying this function to a tree gives a sorted list, then the tree is called a search tree. For instance, our example tree is a search tree because flatten of t is that thing. Search trees have the important property that when trying to decide if a given value occurs in a tree, which of the two subtrees of a node it may occur in can always be determined in advance. In particular, if the value is less than the value at the node, then it can only occur in the left subtree. And if it is greater than this value, it can only occur in the right subtree. Hence, for search trees, the occurs function can be rewritten as follows. This definition is more efficient than the previous version because it only traverses one path down the tree, rather than potentially the entire tree. Should we write that? Let's try writing flatten. So flatten. Oh. How do you like? Oh, does it even? No, it doesn't even need to be. So flatten takes a tree A and returns a list of A's. Okay. Flatten of a leaf. Can we just write it like this? Is x? Oh no, it should be this. And then flatten. Yeah, flatten of a node t1 a, oh, or let's write x t2 is flatten t1 plus plus x plus plus flatten t2. Is it that easy? Is it just gonna work? Let's see. Nope. Type constructor or class not in scope. Oh yeah, you write it like this. Oops. Oh. No. Equations for flatten have different numbers of arguments. Maybe it should be like this. Flatten have Maybe flatten already exists or something? I don't understand. No, flatten does not exist. Why is it? Oh, maybe man, those damn parents. Flatten T. Boom, it works. All right, that's very cool. Yeah, let's do that binary search another time. Okay, we conclude this section by noting that, as in nature, trees in computing come in many different forms. For example, we can declare types for trees that have data only in their leaves, data only in their nodes, data of different types in their leaves and nodes, or have a list of subtrees. Which form of tree is most appropriate depends upon the situation. Note that in the last example, there is no constructor for leaves, because a node with an empty list of subtrees can play the role. Because a node with an empty list of subtrees can play the role of a leaf. 8.5 Class and Instance Declarations. We now turn our attention from types to classes. In Haskell, a new class can be declared using the class mechanism. For example, the class ek of equality types is declared in the standard prelude as follows. Class ek A, where equals and not equals are defined, and not equals is defined as not equal. This declaration states that for a type A to be an instance of the class ek, it must support equality and inequality operators of the specified types. In fact, because a default definition has already been included for the not equals operator, declaring an instance only requires a definition for the equals operator. For example, the type bool can be made into an equality type as follows. An image. Only types that are declared using the data and new type mechanisms can be made into instances of classes. Note also that default definitions can be overridden in instance declarations if desired. For example, for some equality types, there may be a more efficient or appropriate way to decide if two values are different than simply checking if they are not equal. Classes can also be extended to form new classes. For example, the class ord of types whose values are totally ordered is declared in the standard prelude as an extension of the class ek as follows. That is, for a type to be an instance of ord, it must be an instance of ek and support 6 additional operators. Because default definitions have already been included for min and max, declaring an equality type such as bool as an ordered type only requires defining the 4 comparison operators. Derived instances. When new types are declared, it is usually appropriate to make them into instances of a number of built-in classes. Haskell provides a simple facility for automatically making a new type into instances of the classes ek, ord, show, and read in the form of the deriving mechanism. For example, the type bool is actually declared in the standard prelude as follows. Data bool is false or true, deriving ek, ord, show, and read. As a result, all the member functions from the 4 derived classes can then be used with logical values. For example, false is true, false is less than true is true, and so on. The use of : in the last example is required to resolve the type of the result, which in this case cannot be inferred from the context in which the function is used. Note that for the purposes of deriving instances of the class ord of ordered types, the ordering on the constructors of a type is determined by their position in its declaration. Hence, the above declaration for the type bool, in which false appears before true, results in the ordering false is less than true. In the case of constructors with arguments, The types of these arguments must also be instances of any derived classes. For example, recall the following two declarations from earlier in this chapter. Data shape, circle float, rect float float. Data may be A, nothing, or just A. To derive shape as an equality type requires that the type float is also an equality type, which is indeed the case. Similarly, to derive maybe A as an equality type requires that the type A is also such a type, which then becomes a class constraint on this parameter. In the same manner as lists and tuples, values built using constructors with arguments are ordered lexicographically. For example, if shape is also derived as an order type, then we have rect 1, 4 is smaller than rect 2, 3. Tautology checker. We conclude this chapter with two extended programming examples. For our first example, we develop a function that decides if simple logical propositions are always true. Such propositions are called tautologies. Consider a language of propositions built up from basic values false, true, and variables a, b, up to z, using negation, conjunction, implication, and parentheses. For example, the following are all propositions. An image. The meaning of the logical operators can be defined using truth tables, which give the resulting value for each combination of argument values. To save space in such tables, we abbreviate the basic values by f and t. For example, the truth table for conjunction states that a and b returns true if both a and b are true and false otherwise. Using these definitions, the truth table for any proposition can then be constructed in the case of our for example propositions. The resulting tables are as follows. These tables show that the second and fourth propositions are tautologies because their result value is always true, while the first and third are not tautologies because their result is false in at least one case. The first step toward defining a function that decides if a proposition is a tautology is to decide a type for propositions, with one constructor for each of the 5 possible forms that a proposition can have. It's really annoying that there's images in this book. Like, why didn't he just write the code there? Note that an explicit constructor for parentheses is not required, as parentheses within Haskell itself can be used to indicate grouping. For example, the 4 propositions above can be represented as follows. Here's something we can copy. Oh no. Those are just examples. I thought those were the types. Okay. Well, we'll have to reverse engineer them, I guess. In order to evaluate a proposition to a logical value, we need to know the value of each of its variables. For this purpose, we declare a substitution as a lookup table that associates variable names to logical values using the assoc type that was introduced at the start of this chapter. Type subst is an association of characters to booleans. For example, the substitution a is false and b is true assigns the variable a to false and b to true. A function that evaluates a proposition given a substitution for its variables can now be defined by pattern matching on the 5 possible forms that the proposition can have. For example, the value of a constant proposition is simply the constant itself. The value of a variable is obtained by looking up its value in the substitution, and the value of a conjunction is given by taking the conjunction of the values of the 2 argument propositions. Note that the logical implication operator is implemented simply by the less than or equal ordering on logical values. Note that the logical implication operator is implemented simply by the ordering on logical values. To decide if a proposition is a tautology, we will consider all possible substitutions for the variables that it contains. First of all, we define a function that returns a list of all the variables in a proposition. For example, vars p2 is ABA. Note that this function does not remove duplicates, which will be done separately later on. The key to generating substitutions is producing lists of logical values of a given length. Hence, we seek to define a function bools that goes from int to a list of bools, which, for example, will return all 8 lists of 3 logical values. One way to achieve this behavior is to observe that each component list corresponds to a binary number by interpreting false and true as binary digits 0 and 1. For example, the list true, false, true corresponds to the binary number 101. Given this interpretation, we can think of the function bools as simply counting in binary over the appropriate range of numbers. This idea leads to the following definition for bools in terms of the function int to bin, int to list of bits from chapter 7. I don't remember that, but okay. That converts a non-negative integer into a binary number represented as a list of bits. There is, however, a simpler way to define bools, which can be revealed by thinking about the structure of the resulting lists. For example, we can observe that bools 3 contains 2 copies of bools 2. The first preceded by false in each case, and the second preceded by true in each case. This observation leads to a recursive definition for bools. In the base case, bools 0, we return all lists of 0 logical values, of which the empty list is the only one. In the recursive case, bools n, we take 2 copies of the lists produced by bools n-1, place false in front of each list in the first copy, true in front of each list in the second, and append the results. Where BSS, bools smaller or something? Where BSS is bools -1. Using bools, it is now straightforward to define a function that generates all possible substitutions for a proposition by extracting its variables. Removing duplicates from this list using the function rmdups from chapter 7, generating all possible lists of logical values for this many variables, and then zipping the list of variables with each of the resulting lists. Subst goes from a prop to a list of substitutions. Has he defined subst? It's just a pair of oh no, it's an assoc of variables to bools. I don't remember. Subst p is map zip vs. What is that? Oh, where vs is rmdups variables. Okay, yeah. So we zip the variables together with the substitutions. Zip variables. Where variable is rmdups. For example, subst of p2 is a's false b is true. A's false b is true. Wait, so subst. Oh yeah, okay. Yeah, so it's a list of tables that assign the variables to booleans. Finally, we define a function that decides if a proposition is a tautology by simply checking if it evaluates to true for all possible substitutions. Is taut prop to bool? Is taut p? Is and val sp? What has he defined a val yet? Oh yeah, that's like the combination of all the logical operators. I don't really know. S subst p, substs p. What substs? Oh yeah, okay. So S is the List of all substitutions. Oh no, S is one element from the substs of P. And then it evaluates that. And if all of them, whoa, you can do and on a list like that? I didn't know that. Oh yeah, it goes from a list of bools to bool, okay. Because you're not using ampersand, ampersand. Okay, for example, is taught P1 is false, okay. Yeah, I wish I had the images, but I get the gist, you know. I don't know if I'm gonna implement all of this myself. 8.7, abstract machine. For our second extended example, consider a type of simple arithmetic expressions built up from integers using an addition operator, together with a function that evaluates such an expression into an integer value. I hoped he was gonna do like an automaton, but it seems like he's just making a calculator. I don't really understand this example yet. Data expert, you either have a value or an addition. What? This is so boring. The previous example was way rare. Note that the definition of the value function does not specify that the left argument of an addition should be evaluated before the right, or more generally, what the next step of evaluation should be at each point. Rather, the order of evaluation is determined by Haskell. If desired, however, such control information can be made explicit by defining an abstract machine for expressions. Aha, here we go, which specifies the step-by-step process of their evaluation. To this end, we first declare a type of control stacks for the abstract machine, which comprise a list of operations to be performed by the machine after the current evaluation has been completed. Type cont, control stack, I guess, is a list of operators, and data op is either eval expert or add integer. The meaning of these two operations will be explained shortly. We now define a function that evaluates an expression in the context of a control stack. That is, if the expression is an integer, it is already fully evaluated, and we begin executing the control stack. If the expression is an addition, we evaluate the first argument, x, placing the operation eval y on top of the control stack to indicate that the second argument y should be evaluated once evaluation of the first argument is completed. In turn, we define the function that executes a control stack in the context of an integer argument. That is, if the control stack is empty, we return the integer argument as the result of the execution. If the top of the stack is an operation eval y, we evaluate the expression y, placing the operation add n on top of the remaining stack to indicate that the current integer argument n should be added together with the result of evaluating y once this is completed. And finally, if the top of the stack is an operation add n, evaluation of the two arguments of an addition expression is now complete, and we execute the remaining control stack in the context of the sum of the two resulting integer values. Okay, I don't really get it, but finally, we define a function that evaluates an expression to an integer by invoking eval with the given expression and the empty control stack. Value expert int. Okay, the fact that our abstract machine uses two mutually recursive functions, eval and exec, reflects the fact that it has two modes of operation, depending upon whether it is being driven by the structure of the expression or the control stack. To illustrate the machine, here is how it evaluates 2 plus 3 plus 4. Value. Add val. Applying value. Wait, so value. Okay, just Oh, okay. So value just adds a control stack and runs the eval function. Okay. Then eval applying eval. Okay, so okay, now it moved. Wait, so the top. So we have a tree here, and the left side of the tree is another expression, and the right side of the tree is a value. Eval. So it moves this chunk. How do you say that expression onto the what is it called? Stack. Control stack. Applying eval. Wait, but why? Wait. Ah, man, it's really annoying that I don't have these images. I could just open this book in the browser, but I started recording, so. Okay. Eval. Move that over there. Applying eval. Oh, so it just so eval transforms the list into a control stack, and then exec calculates the result of the stack. Is that how it works? I don't understand. No, so it does go like back and forth. Like, why is exec of? I don't know, dude. Is this some like RPN? Is this related to? I mean, this is just not PN. I mean, how do you say that? Not reverse, but just Polish notation. I don't know. Okay, note how eval proceeds downwards to the leftmost integer in the expression, maintaining a trail of the preceding right-hand expressions on the control stack. In turn, exec then proceeds upward through the trail, transferring control back to eval and performing additions as appropriate. 8.8 Chapter Remarks. The abstract machine example is derived from a source, and the type of control stacks used in this example is a special case of the zipper data structure for traversing values of recursive types, as well as the basic mechanisms for declaring new types and classes introduced in this chapter. The GHC system also supports a number of more advanced and experimental typing features. Exercises. I don't think I'm gonna do, maybe another time, you know. Chapter 9. Okay, so I think we got through like the most basic theory, because now he's going with the next chapter is like a practical example. So I think maybe I'm gonna study like, how do I go? Oh my God. Okay. Oh no. Okay, I don't know how to scroll back. I think my plan is, now that I have the basics, maybe I should like make something bigger, or maybe learn an interesting language. Like I'm really interested in Parsec, or maybe like FRP, like Yampa. We shall see.